Hi everyone, welcome to Krish Chemistry. So this is the class of F block elements. I am going to explain you this whole F block elements in only 57 points. I am going to cover every previous year question. If you just see this video only, right? So you don't need to revise F block elements again, right? So every previous year question, every important point I'm going to discuss in this video. Okay, you don't need to worry about F block elements. This is very useful for your revision and very useful for your exam. Even though you are preparing for CSR, net, GATE, BARC, any exam, this F block elements is important topic and important lesson. So listen carefully. Okay. Okay. So these are the slides. So totally, if you see, totally 57 points are there. Right? Totally 57 points are there. If we can discuss these 57 points in a detailed manner, this is more than enough. You don't need to revise anything. Okay. So let us start. So the first one is general configuration of F block elements. So what is the general configuration? N minus 2 into F power 1 to 14, N minus 1 into d 0 power d power 0 to 1 and ns power 2 bus. Okay, so this is the answer of first question. Second, actinides are unstable. Okay, so actinides are unstable. Why? Generally actinides are unstable due to radioactive decay. Okay, except but all actinides are unstable due to radioactive decay only except thorium 232, thorium 232 and uranium 238. Uranium 238. So among all actinides, only thorium 232 and uranium 238 are stable, since this T half means half life of these two elements are very high, right? Half life is very high of these two elements. So remaining actinides, if you see, those half lives are not high. Okay, so that's the reason why remaining actinides are not stable due to radioactive decay, but these two elements are stable because T half of these two elements is very high. So next one, if you take boron and carbon, okay, so which is more stable? How can you decide? See, for suppose, so the important rule you have to remember here, element with even number of protons is more stable than odd number of protons, right? So for suppose if you take boron, so boron 5 here, mass number 10, carbon 6, 12, right? Here 5 protons are there, here 6 protons are there, here 6 protons are there. So the element with even number of protons is more stable than odd number of protons. Why? Because the element with odd number of protons having 2 or more than 2 isotopes, right? So that's the reason why the element with even number of protons is more stable. So in this two, so carbon is more stable than boron. Okay, so next, magic numbers. These are called magic numbers. So 2, 8, 20, 28, 50, 82, 126. These numbers are called magic numbers. You have to remember these numbers, very important for your exam. For suppose, if number of protons or neutrons, okay, are there in this range of numbers, right, then your nuclei will be very stable. For suppose I am taking lead, Pb 82 208, okay, 82 208. So if you see number of protons 82 there here, yes, 82 is there. And if you see number of neutrons 208 minus 82, so that is number of neutrons are 126, number of neutrons 126, so 126 is also there here. So 82 and 126 are there in this range, in this magic numbers. So this nuclei is the very stable, right? So next next important point, if you take lanthanides, you have lanthanides, cerium, praseodymium, neodymium, promethium, samarium, europium. Among all these lanthanides, okay, generally if you take, all lanthanides are naturally occurring. Every lanthanide, almost all lanthanides are naturally occurring except one element, that is promethium. Okay, only promethium. So next, lanthanum. Okay, so in total lanthanides, lanthanum is there. I'm asking you whether lanthanum is F block element or D block element. Lanthanum is D block element, not F block element, because after lanthanum 57, F block series will start, right? So only cerium to lutetium, okay, are F block elements. Lanthanide comes under D block element. Next, common oxidation state for lanthanides. What is the common oxidation state? +3 oxidation state is most common oxidation state for lanthanides, right? So sometimes +4 is also stable, but most commonly +3 oxidation state is more stable. Next, cerium +4, terbium +4, europium +2, and ytterbium +2. Okay, so these four are very, very stable. Generally, +3 of lanthanides is stable, right? But even though +4, +4, +2, +2 stable. What is the reason? Because if you see cerium +4, if you know the electronic configuration, okay, I will tell you how to remember, how to memorize electronic configurations. But before that, see, if you take cerium +4, so 4f0, 4f0, 5d0, and 6s0. 6s0. If you see, all orbitals are empty, right? So that means no electron repulsions are there. So this is stable, right? If you take terbium +4, right? So 4f7, 5d0, 6s0. 4f7, 5d0, 6s0. Okay, so f orbital is half filled, and here d0, s0. So this is also stable. Next, europium +2. Europium +2. 4f7, 4f7, 5d0, again 4f7, 5d0, 6s0, stable. Okay, so next one is ytterbium +2. 4f14, because these two are half filled, right? 4f14, 4f14, 5d0, 6s0. This is completely filled, so this is stable. Okay, so generally lanthanides are stable in +3 oxidation state. Common oxidation state of lanthanides are +3, but this cerium, terbium, europium, and ytterbium are stable in these oxidation states also. Next, cerium +4 is what? If you take cerium +4 is good reducing agent or good oxidizing agent. What? Generally +3 oxidation states are more stable than anything. So if we have the +4, then generally it will try to reach +3 oxidation state always, because this is the lanthanide series. Okay, this element belongs to lanthanide series. So cerium +4 will take electron and convert to +3. It is taking electron, so reduction. So cerium +4 is a good oxidizing agent. Good oxidizing agent. Okay, cerium +4 is good oxidizing agent. Important. So next, if you take ionization energies, okay, so ionization energies of transition elements compared to the lanthanides. Ionization energy of transition elements is high or lanthanides is high? Answer is ionization energies of transition elements is very high. Why? If you take transition elements are very, very low in size, less in size. But if you take lanthanides, big in size. Okay, so if you take charge density equal to charge by size, right? That means effective nuclear charge, we can write effective nuclear charge equal to charge by size. So that means this effective nuclear charge is inversely proportional to the size. Okay, so if you take the transition elements, size is low, that means effective nuclear charge is very, very high. Okay, so whenever effective nuclear charge is very, very high, it is very, very difficult to leave the electron. Okay, if you want to remove the electron from this element, you have to give very, very high energy. So that's the reason why ionization energy. Ionization energy means the energy required to remove an electron from the outermost shell. Whenever this effective nuclear charge is very, very high, that means it is not that easy to remove the electron from this element. So ionization energy of transition element is greater than ionization energy of lanthanides. Okay. So next, for lanthanides and actinides, what is the magnetic moment? What is the magnetic moment? So for lanthanides and actinides, the magnetic moment formula you have to use Z root over Z into Z plus 1. Okay, Z root over Z into Z plus 1. Why? Because see, for suppose I have the nucleus here, right? Here 4f orbital is there. Here 5d orbital is there. Here 6s orbital is there. Here ligand is there. Okay, so this 4f orbital is very near to this nucleus. Okay, so effective nuclear charge of this nucleus on this 4f is very, very high. So this is deeply buried. Okay, so this is deeply buried in nature. So therefore this ligand will interact with this 5d and 6s orbital only, not 4f. So whenever the ligand is not interacting with 4f, whenever ligand will interact with 4f, then orbital quenching will be there, like in transition elements. But here ligand is not interacting with 4f. So that's why orbital quenching cannot be observed. Okay, so that's why we are using this formula. Okay, because J equal to L plus S, right? Orbital motion will be quenched in transition metals. So that's why in transitional metals we use mu equal to root over n into n plus 2, but here we use J equal to L plus S to L minus S. L term will be, orbital motion means L term will be introduced here, because this ligand is not interacting with this 4f orbital of metal. Okay, so next one is, so for lanthanides and actinides we have to use this formula. Next, europium plus 3 calculated magnetic moment and experimental magnetic moment. If you take europium plus 3, what is the calculated magnetic moment and what is the experimental magnetic moment? So the calculated magnetic moment for europium plus 3, mu equal to 0. You can take electronic configuration and fill the electrons, you will get this, mu equal to 0. Okay, and if you take experimental 3.32, 3.32, 3.5 B. Okay, so remember these magnetic moments if you can, right? Very, very important. These two magnetic moments are very, very important. Next, for samarium plus 3, calculated magnetic moment is 0.85. Calculated magnetic moment is 0.85 and the experimental magnetic moment is 1.42 to 1.7 bm, Bohr magnetron. Okay, next, if you take the sizes, okay, so size difference of 4d and 5d elements low compared to 3d and 4d. So what is the reason? Okay, if you take, for suppose, vanadium, zirconium and hafnium, right? This is 3d element. So the size difference between this and this is high, but this and this is almost similar. The sizes of zirconium and hafnium, that means 4d and 5d elements, are almost similar. What is the reason? So when it comes to here, f orbital involves. Okay, f orbital, because this f transitions, f series will start from here. So whenever f orbital is introducing here, because of poor shielding effect, of 4f, size will decrease. Okay, shielding effect decrease, size decrease. So because of poor shielding effect of 4f orbital, the size will decrease from 4d to 5d. Okay, so answer is due to poor shielding effect. Poor shielding effect of 4f. Shielding effect of 4f. Okay, next. Basicity of hydroxides of lanthanides. For suppose, if you take one lanthanide, LaOH tries. Okay, next cerium OH tries. If you take hydroxides of lanthanides like this, so what is the basicity order? This is the basicity order. LaOH tries greater than COH tries greater than something up to lutetium. What is the reason? Because if you move from lanthanum to lutetium, what happens? Size decrease. Okay, so whenever size decrease, effective nuclear charge will increase. Okay, so when effective nuclear charge will increase, you cannot remove this OH that easily. Yes or no? Right? So that's the reason why basicity will decrease from left to right. Okay, so next separation techniques are there to separate the lanthanides, so you can read by yourself. Okay, so these are not that important, but have a look once. Right? Next one is partition coefficient. So the partition coefficient formula: solubility in organic phase over solubility in aqueous phase. If you take this partition coefficient, this partition coefficient, if you move from left to right side, this partition coefficient of right side element, that means smaller size element if you take, okay, so lutetium etc is higher. That means partition coefficient among all lanthanides, lutetium partition coefficient is very very high. Okay, so next next, so how you have to remember the electronic configuration? So electronic configuration, if you see 4f 5d 6s. Okay, so the first one, if you observe lanthanum, so lanthanum 4f 0 5d1 6s 2. So what is the trick here? I have already explained electronic configurations. You have to remember. If you can get to know the electronic configurations, if you can remember the electronic configurations, you can easily find out the colors also. What is the trick here? So trick of for f orbital. Okay, if you take the lanthanum, first of all, here 0 d1 s2. Next cerium f1 4f1 5d1 6s2. Next praseodymium, neodymium up to lutetium. So if you take from lanthanum to lutetium, only F2 and F8 are absent. Okay, F2 and F8 are absent. Remaining all F0, F1, F2, F3, F4 all will be there, but only F2 and F8 are absent. And again 7, F7 will come 2 times. Okay, F7 will come 2 times. That means if you take europium 4F7 5d0 6s2, gadolinium 4F7 5d1 6s2. Okay, for europium and gadolinium we can observe 4F7, and 14 also come 2 times. That is for ytterbium and lutetium. Ytterbium electron configuration 4f14 5d1 5d0 6s2, for lutetium 4f14 5d1 6s2. Okay, so 7 2 times, 14 2 times. And if you take d1, d1 4 5d1 is for lanthanum and 5d1 is for cerium, and also 5d1 is for gadolinium and 5d1 is for lutetium. Okay, for all elements s orbital is fully filled. S orbital is fully filled. Okay, you can read this electronic configuration in any book. Next, for lanthanum plus 3, gadolinium plus 3 and lutetium plus 3. Right. So what is the magnetic moment formula? What is the magnetic moment formula? Because if you take lanthanum plus 3, 4f0, 4f0, 5d0, 6s0. Okay. If you take gadolinium plus 3, 4f7. Okay, 5d0, 6s0. Lutetium plus 3, 4f14, 5d0, 6s0. This is empty. This is half filled. This is completely filled. That means electronic transitions are not possible here. Okay, so in this case, you can, so whenever, if you take the electron configuration like f orbital, 7 f orbitals, okay, you take 7 of f orbitals and fill this 0, 7 electrons, 14 electrons, you will get L is 0. Okay, so when this L is not there, you can use directly this formula, mu equal to root over n into n plus 2, like transition elements. Okay, for these 3 elements, to calculate magnetic moment, you can use this formula directly. Next, LnH2, lanthanum hydrates. Next, LaI2, okay, lanthanide iodide. Next, cerium iodide exists and ఎలా exist? How these will exist? Okay, metal hydrates. Okay, if you take LnH2, LnH2, LnH minus twice. LnH2 exists like this. LaI2 exists like this. Right? Next, cerium iodide exists like this. Why? Because in LnH2, Ln is in +2 oxidation state, but +3 oxidation state is more stable. So that's why these compounds will exist like this. Okay, now it is in +3 oxidation state. Okay, so that's the reason why. So these are called metal hydrate. This is the metal iodide. Okay, next, if you take left to right, what happens? Size decrease. When size decrease, coordination number depends on size. So when size decrease, coordination number also decrease. Okay, next, if you take LnF3, for LnF3 coordination number is, for LnF3 lanthanide fluorides, coordination number is 11. Geometry, pentagonal, pentacapped, trigonal prism. Pentacapped, you have to remember this, pentacapped trigonal prism. Trigonal prism, right? Next, for LnCl3, what is the coordination number? Whenever we are going from left to right, size decrease, so coordination number decrease. So here you have to remember in 2 steps. So the first one is from lanthanum to gadolinium. Okay, coordination number 9. Okay, and geometry is coordination number 9. Geometry is whenever we have 9, tricapped trigonal prism. Tricapped trigonal prism. Trigonal prism. Okay, so next, if the element is from terbium to lutetium, terbium to lutetium, then coordination number is 6. Coordination number 6. Geometry is octahedral. Okay, because size is decreasing, so coordination number is also decreasing. Okay, very important. This is very important. Next, hydrates. If you take GDX3 6H2 or TBX3 6H2 or lutetium LuX3 6H2, if you take this type of hydrates, then coordination number, you have to remember, only you have to consider here 6H2O and 2 halogens. That means the coordination number for this hydrates is 8. Coordination number is 8. Next, complex formation stability of F block elements. What is the complex formation stability? Maximum coordination number of F block element is greater than 6. Okay, so generally F block elements, if you take, are size of the F block elements are higher than D block elements. Okay, so these are very labeled. So because of the higher size, so these compounds F block elements can form greater than 6 coordination number complexes, right? Next, NO3 minus, CO3 2 minus, SO4 2 minus. These are called as bidentate ligands. Bidentate ligands. Why? So these ligands generally behave as bidentate ligands when they combine with lanthanides due to larger size. Okay, so that means bidentate ligand means, so every ligand will give 2 electrons. For suppose if you take this complex, what is the coordination number of this complex? If you see H2O 5, that means 5, right? Next, NO3, this is the bidentate ligand, right? This is the bidentate ligand. So 3 2 is 6, 6 plus 5, 6 plus 5, 11. Next, ethylene diamine tetraacetate, and here 3, here 6, ethylene diamine tetraacetate, because 2 oxygens, 4 nitrogens, H2O 3, totally 9. So coordination number of this complex is 9. Next, GDCl4 THF twice. Okay, tetrahydrofuran only monodentate. So here 2, so 2 into 1 2 plus 4. So coordination number is 6. Next, NO3 4 times, PH3 PO twice. 4 2 ja 8 because this is the bidentate ligand. So 4 2 ja 8. Next pH3PO monodentate 2 into 1 2. 8 plus 2 10. So coordination number is 10. Next CgNO3 6 times minus 2. Here 6 2 ja 12. Coordination number 12. CeCl 6 times minus 2. So here the coordination number is 6 only, right? Next, the coordination number, if coordination number is 8 and the ligand is acetyl acetonate, what is the geometry? Geometry is square square anti-prism, square anti-prism. Okay, next 4f to 5d broad peaks. So whenever you have this d orbital, okay, you will always get broad peaks. Okay, so f to f always give sharp peaks. Okay, f to f always give sharp peaks. Why you will get broad peaks when you have d orbital? Due to vibronic coupling and John-Teller distortion. Okay, due to vibronic coupling and John-Teller distortion, when you have the orbital, then you will get broad peaks. Okay, but in F2F no interaction of ligand because 4f is deeply buried. Why these are sharp peaks? Because 4f is deeply buried. Okay, next F0, F7 and F14, F30 are colorless. Why? F0, F7, F14 are colorless because transition is not possible. Okay, they are spin forbidden. Transition is not possible because this is empty, this is half filled. F14 is fully filled. So whenever transition is not possible, they are colorless. This is the first thing. Why F13 is colorless? F13 is colorless. Okay, so you have to remember this. F13 is colorless, you have to remember, but F0, F7, F14, they are colorless because transition is not possible and they are spin forbidden. Okay, next F1 is also colorless because 4f to 5d transition. Okay, because of 4f to 5d transitions, F1 is colorless. Next, cerium +4 with highest oxidation state, because +4 is highest oxidation state here. The color of this cerium +4 orange yellow color due to ligand to metal. Whenever metal is in +4 oxidation state, so ligand will donate electrons to this. So due to LMCT, it will get orange yellow color. Samarium +2 blood red color due to MLCT, because oxidation state is less, so that it will give electrons to the ligand. So due to MLCT, it will give blood red color. Very, very important. Next, shift reagent. What is the shift reagent? To spread out NMR spectrum, we use generally shift reagents of beta diketone complexes of europium +3 and praseodymium +3 instead of increasing magnetic field. Okay, so generally to spread out any spectra, we increase the magnetic field, but instead of increasing magnetic field, we use this also. Okay, so EU DPM tries and EU FOD tries. So what is EU DPM tries full form? So europium 3 tris 2266 tetramethyl 3,5 heptone dionate. Okay, and this EU FOD tries will be called as Siever's reagent. Okay, so remember these two things also. Next, color of lanthanides, trick is there. If you observe chemical bonding playlist, in chemical bonding playlist I have given one trick of lanthanides. You can watch that, you can easily understand, right? Next so next one is for cerium +3 and dysprosium +3, only ground state J level is populated at room temperature. Okay, so if you take cerium +3 and dysprosium +3, ground state J level is populated at room temperature. For europium +3 and samarium +3, excited state and ground state both J levels are populated at room temperature. Right, very, very important. These are previous year questions. Complexes of lanthanides are rarely show isomerism. You have to remember this. Next, metallic radii of europium and ytterbium are very, very high. Right, metallic radii of europium and ytterbium very, very high. You have to remember this. Next, Cerium pH3 pivot twice, NO3 4 times minus. What is the coordination number? Here bidentate, so 4 to 8. Here 2 1 2, so 8 plus 2 10. Okay. Next, gadolinium plus 3, lutetium plus 3, lanthanum plus 3 has similar spin only and calculated magnetic moments. This is also very very important and previous year question. Covalent radii of 4D and 5D elements are almost similar in size because why? 4F is deeply buried. I have already discussed this point. Next, U3O8 is most stable oxide of uranium. Okay, very very important point. Next, gadolinium plus 3 has isotropic magnetic susceptibility. This is also previous year question. Next, europium plus 3 exhibit color in aqueous solution. We have to remember this. Cerium plus 3 color, generally it is a colorless. Cerium plus 3 is colorless due to F2D transition. Cerium plus 3 is colorless due to F2D transitions. Next, in actinides, only thorium and uranium are naturally occurring. Okay, in actinide elements, only thorium and uranium are naturally occurring. Next, the source is monazite sand. Okay, thorium source is monazite sand. Uranium source pitch black. UO2 plus, this is in plus 5 oxidation state. UO2 plus 2 plus 6 oxidation state, right? So UO2 plus 2 you can write like this, U double bond O plus 2. Linear structure, yes or no? So this is dioxo ion, this is oxo ion, this is dioxo ion. Next, UO2 NO3 twice, H2O twice, coordination number 2 2 is a 4, 5 6 7 8, so coordination number is 8, hexagonal bipyramidal geometry, right? Next, UF6 and UCl6 are octahedral geometry. Okay, so this is about F block elements. So these points are more than enough. These points are more than enough. You don't need to study anything after this video. Thank you so much for watching. All the very best.